know when the grades are available, so you don't have to keep checking. Also, I want to remind you, a couple days ago, maybe last week, Seth came in a few years, Seth Alexander talked about an ultrasound opportunity for you guys. I'll resend that link for you if you want to sign up. If you're not aware of it, this is not the giant ultrasound machine that you deal in, and it's like 100-year-old technology. There's sort of a new way of using ultrasound called point-of-care ultrasound. For those of you who are going to medical school or PA school, you'll be using these in your training. It's something you can plug into your phone and scan people right where you are, and take a look at their anatomy. Cool stuff. As far as we understand, it's really hasn't really been used much at the undergraduate level, so we're going to try to see if there's any utility in doing that. One day we'll probably bring it into the 253 lab if it works out okay. Anyway, I'll send out a link for that as a reminder if you want to sign up. I think we've got people who want to be scanned, go figure. But for those of you, if you're interested in learning how to scan somebody and interpret what you're looking at, might be a good opportunity. Okay, otherwise, let's get going here. We've got a fair number of things to get through. I did want to tell you one thing that we're going to be doing that's a little different than the reading schedule. I did not include in your reading the first little section, which was a very broad orientation to the respiratory system. I know you've had that already, but I'm going to cover some of that material today, so this is not entirely all on your reading. But I would encourage you all to go back and look at that, especially if you're feeling a little bit underprepared as we go into the respiratory system. I know that in the previous anatomy physiology course, some of you have had varying levels of preparation to prepare this system. So let me start off by giving a brief summary of what's going on in sort of the terminology surrounding the respiratory system. Okay, so first off is ventilation, and respiration and ventilation are sometimes used interchangeably, but really ventilation is the specific term we use to describe the movement of air. Okay, so not gases in particular, but the movement of air. Okay, so this is your breathing in, breathing out. Okay, then the air that's in your lungs, and here we're showing an alveolus, which is the single unit for respiration. Inside your lung, you have these alveoli, and it's there that the air that you've inhaled through ventilation has gases that are moving into the body. Okay, so this is gas exchange. We are moving gases. Okay, so we can think of ventilation as moving air, and respiration as moving gases. Okay. All right, simple enough, and we should end it right there, right? Unfortunately, there's more. So then we have to transport our gases, right? And we're going to spend a whole lecture on this in a few days. Okay? How do we carry carbon dioxide and oxygen in the blood cells, and so on? Okay? Ultimately, we're going to exchange these gases another time, but this time with at the level of our systemic capillaries, right? We've learned about systemic capillaries before with the previous coursework, right? But now we're going to talk about how these gases actually move, okay? Carbon dioxide and oxygen, right? And then lastly, what's the point of all this, right? We have cells that are using oxygen. We'll talk about how that happens. This is called cellular respiration. No, we're not going to dive into the hairy details of this as you've learned about in Biology 101, but that's where all the stuff is going, right? This is what's happening. Cells are using oxygen, and as a byproduct, they're making CO2. Okay. Then the blood comes back around, and we exchange the CO2, right? So these are the processes. Up here, number 2 and number 4, gas exchange. These are both referred to as respiration. Okay. One of these is sometimes called external respiration, one is internal respiration. Are those familiar terms to you? Maybe? Okay. Where do you suppose external respiration would take place? Number 2 here at the top, with the air that's coming in from the atmosphere. So this is exchanging gases with the gases that exist outside of the body. Okay, and then internal is simply exchanging the gases between blood and our tissues. All right, where we're going to focus today, I'm going to give you a little bit more overview, but we're going to be focusing mostly on ventilation today. Okay. So just that one subset. Okay. So you've seen pictures like this before, right? And back in anatomy lab, you learned about the various divisions here, right? All this should look pretty familiar. One thing I want to point out is that there are two broad categories of airways. Okay? We have something called the conduction zone and something called the respiratory zone. Who can tell me what the conduction zone is, what its purpose is? It's a pathway for the air. Yeah, so this is, we're moving air in and out of the lungs, right? And there are all these airways from the nasal cavity on down to the trachea, the bronchi, the bronchioles, all of these structures that you've learned about, where we're just conducting air, we're moving air, okay? And then what do you suppose the respiratory zone is concerned with? Respiration, okay? That is gas exchange, right? So at the very end of our bronchioles, we have a series of bronchioles that have something attached to them, okay? And these are the alveoli, okay? And then this whole process of, or whole structure of branching ends with alveolar sacs, okay? So all of these structures here at the bottom of the respiratory zone, they have alveoli attached to them. Alveoli are necessary for respiration, that gas exchange, okay? So, what does that mean if we're talking about a molecule of oxygen up here in the bronchus? Is it undergoing respiration? Any gas exchange? No. Okay. So the gases that are moving through the respiratory system, if they're in these larger airways, the conduction zone, they're not being brought into the body, that is, into the blood, right? They're just simply passing through. Once they get down to the alveolar sacs, that's where the action is, right? Okay, simple enough. All right, I want to tell you a little bit about the cells that are involved. All of that conduction zone, nasal cavities on down to the bronchioles, they have a very particular histology, okay? And the cells here that form the boundary are the epithelial cells. Okay, so here we're going to refer to this as the lumen. You've heard this term with regard to capillaries and blood vessels, right? What is a lumen? How would you define that? An open space, right? So the inside of something. So in blood vessels, the lumen is filled with blood. In your GI tract, it's filled with lunch. Okay. Here, what's in your liver? Air, right? Okay. So the cells here that form the boundary, these are epithelial cells. Okay. You've learned about epithelium before, and in particular, it's called the this type is usually called the respiratory epithelium. Okay. It's a very unique type of cellular arrangement, only found here. Okay. We don't find it anywhere else. It's known as a pseudostratified columnar epithelium. Okay. So here's a stretch. I don't know if anybody knows this. What does it mean to be pseudostratified? Yeah.
They're like kinda in like bands that go down.
They kind of look like they're in layers, right? So if you look at those little purple dots, they're all the nuclei, right? She's right. It looks like there's kind of different layers here. But for all these cells, for every cell, it reaches all the way to the top and all the way to the bottom. Okay, so really it's just one layer of cells. Okay. Why is it like this? Nobody knows. Okay. But this is a very unique characteristic of the pseudostratified epithelium. Okay. The other thing that's here is if you take a look at the surface, what do you see on the top of those cells? see anything there? It's a little hard to see. Squint. You're squinting? What is it?
Are they villi or something?
That's a good guess. It's not villi. What is it? Cilia. Okay? A villus is kind of a multicellular structure. These are little extensions of the cell membrane. Okay? Some of them have been lost here, so it's a little hard to see in this section. But what do these things do? Why do we have cilia here? What's writing on top of those cilia? Mucus, somebody said, very good. So we got this big blob of mucus up here, okay? And what do the cilia do? They move that mucus, right? Okay. So all of the conduction airways have this respiratory epithelium with cilia, and they secrete mucus, and little particles of air are moving through here, or particles of dust, rather, and other suspended things in the air, and they get stuck. Okay? And what happens is that all of these, all of the airways propel the mucus in the same direction. Okay? So they've got a polarity to the way that they're moving. Their cilia, and they have the effect of pumping or moving mucus, right? So all those little critters get stuck here. Might be bacteria, whatever, and they all get propelled upward. Okay, and finally it ends up in the back of your throat, and you usually swallow it without realizing it. Okay, and this is referred to as the mucus elevator. Sounds fun, right? Okay. So to draw a little connection to something that might be useful going forward, let's talk for a brief moment about cystic fibrosis. Anybody here know anybody with cystic fibrosis, or yikes? Wow, lots of you. Okay, not surprising. What do you know about cystic fibrosis? They get sick a lot. Yeah, they're very prone to infections. What else do they have?
They're like fluids are the wrong consistency?
Yeah, they have the fluids, especially in the airways, are the wrong consistency, and in particular, they're too thick or viscous. Yes, and so they have difficulty breathing or clearing their mucus, and because they're not able to clear the mucus, they are prone to infections. Right? So this mucus elevator that we talked about would be pulling bacteria and stuff out of your airways, right? But if it's stagnant, if it's not moving, what happens? Those bugs are allowed to proliferate and dwell there. So I promised you guys last time that we'd come back to this concept of epithelial transport. So here we are. You're welcome. I want to sort of give you the background behind cystic fibrosis, but in the process, discuss this topic that we've neglected so far. So epithelia, as you've learned about, they form sheets or tubes, right? And they've got polarity, meaning a difference. Okay. So what do we see at the top here that's not found at the bottom of the cells? Microvilli, okay, or cilia. Okay. Those microvilli or cilia are little extensions of the cell membrane. Okay. And this membrane here at the top is referred to as the apical membrane, and we refer to this side as the apical side of the epithelia. Okay? So all epithelia have an apical side, okay, with an apical membrane. They usually point towards a lumen. Okay? So in your GI tract, they're pointing towards your food. Okay? In your airways, they're pointing towards the air. In your blood, they're pointing towards your blood. All right. Okay, so we have an apical membrane, and then down below we have the basolateral membrane. Okay, so these cells are all packed together and tight. They've got membranes that surround the entire cell, obviously. But the top side is apical, the bottom side is basolateral. Okay. So if the apical side faces the lumen, the basolateral side faces connective tissue below. Okay. So what separates these two? Well, there's a group of proteins here that connect cell to cell. And these are made of tight junctions. Okay, so somewhere in here, actually this picture is trying to show you this little squiggly stuff here, right? It's sort of like a belt surrounding these cells. The membrane has all these tight junctions that lock cells, neighboring cells together. Okay? And one of the things they do is they keep these membranes different. These membranes have specific proteins that are found in the apical side, not found in the basolateral side, and vice versa. One of the most important proteins that we're going to keep coming back to in this course as we learn about the cell biology behind physiological processes that are sodium-potassium pumps. Okay? Sodium-potassium pumps are always in the basolateral side. Okay? And with regard to respiratory epithelium, we have a very important active transporter here for chloride. Okay? So we have a chloride active transporter. Okay. And it's found in the basolateral side. With me? Okay. All right, so let's talk about mucus then, right? Mucus? Anyone? Oh, there we go. Okay. All right, how do we make mucus? Well, mucus is made of mucins, okay? And mucins are sort of a generic name for molecules that are proteins and glycoproteins and glycolipids, right? A series of molecules that are exocytosed from the cell. Okay, so we spit these little things out into the lumen, okay, and we mix with it water. Okay, so mucus is water plus the mucins, right? You need both of those in order to make mucus of the right consistency. Okay, where do we get water from? Well, this is where the chloride transporter comes in. Okay. So if we actively transport chloride into our cells, basolateral side, who can tell me what's going to happen to the chloride concentration in and outside of the cell? First off, where do we have lots of the chloride? Chloride ions are high where? Outside the cells. Okay? And we are able to pump chloride into the cells. This is an active transporter. So what's going to happen to the chloride concentration in the cell? It's going to increase. Okay? Will it reach an equilibrium and stop, or can it go beyond that? What do you think? If it's an active transporter, what's going to happen to chloride levels inside the cell? Are you raising your hand? You stretching, right? Yeah, it's good point. So we're going to have very high chloride levels. It can go actually beyond the concentration we find outside of cells. Okay? So it can be very, very high. Okay? And then we have a chloride transporter here that works through the process of facilitated diffusion. Okay? Somebody remind me what that means. Facilitated diffusion means what's going to happen at that channel. Get back to maybe first or second day of class. Facilitated diffusion. What's going to happen to our chloride here at the top of the apical membrane? It's going to travel through. It's going to be transported out. Okay, downwards concentration gradient. Okay. So because we're pumping chloride in at the basolateral membrane, we're able to exude chloride from the top, right, through the apical membrane. Okay. All right, so we've got chloride, big deal. So what's going to happen if we start pumping a whole bunch of chloride out into the space? I'm going to keep drawing these negatives so you can tell me what's going to happen. It's going to be negative, right? You're going to develop a negative charge, okay? So what happens as a result of this is that sodium, or prime sodium in the extracellular fluid, is going to leak through the space between cells and accumulate along with chloride. Okay. And what's the next step? If we put all this sodium chloride out there, what's going to happen? Osmosis. Very good. So we have aquaporins, little channels that are found in most cells of our body, right? And we're able to pull water through. Okay? So this whole process of taking chloride, pumping it into the cell, the basolateral membrane, comes out the other side, right? Through passive fusional forces, right? Results in sodium coming across for electrical reasons, and then water through osmosis. Okay? So these are all the same phenomena we've learned about, right? And we're just going to be applying it here to understanding how we make mucus, right? So we've got mucins, which we secrete through exocytosis, and then we have this rather complicated way of getting water out there as well. Okay. All right, so this seems fairly complicated. Why do we do this? Do we have any other way of moving water? Aquaporins allow us to move water, right? And osmosis is really the only way we have to move water. Okay, and we'll see this again and again as we go through the course. If we're going to move water somewhere, we do it through osmosis. There's no water pump to push it. We have to push the ions, and then water follows. Okay. So let's see if we understand where we're headed here. You saw the exam last week, you know I like these types of questions, right? So take a moment here, let me read this. Individuals with cystic fibrosis have a mutant, non-functional, apical chloride transporter. Okay? Which of the following is going to be an accurate description of what these people have? Fire? See what you, oh man, we don't even need to talk about this one. But let's run through it, make sure not everybody here is quite on the right page. So let's help our classmates here. What do you think?
Okay, so the apical transporter is the first one that's memory. So chloride still being transported into that cell, but it's not transported into the.
Okay, hang on there. So she said that we're going to be still pumping chloride into the cells, right? So it's going to accumulate intracellularly, but it's not going to go into the lumen, right? Because the apical membrane is the one at the top, right? Okay. All right, so without the accumulation of chloride, we're not going to be drawing sodium into the lumen. Okay, great. I had a question over here about aquaporins. Water can move through aquaporins. It doesn't have to go through that path alone. We can actually get a little bit of water slipping through the tight junctions, depending on how tight they are. We'll talk later. We have tight junctions in the body that are tight, and we have not so tight junctions. And the strange thing. We'll talk more about that. But is water going to accumulate if chloride and sodium don't accumulate? No. Water's not going to move. Those channels, those pores for water will be open, and water could move through them, but there's no osmotic pull to the extracellular. Yeah?
Does the water follow the sodium to the airway movement, or does it follow both the chloride and the sodium?
It'll follow both. Both are osmotically active particles, as we've talked about. So chloride alone will draw water, but chloride and sodium will draw twice as much. Yeah. Yeah.
So since the water can't mix with the mucin,
Mhm.
is that why the mucus doesn't move?
Right. So thank you for bringing that up. So the reason, when we talk about cystic fibrosis and we have that inactive chloride channel in the apical membrane, the reason that they have that thick mucus that doesn't move effectively is that we're not drawing water out. Okay. So it's not that we need chloride per se to get fluid mucus, but we need the water that chloride drives. Okay. All right, great. A couple of things we can talk about here in terms of background information, things that I want you guys all to be familiar with. The path of blood, we've learned about this. We talked about this extensively with the systemic circulation, but just so we're all on the same page. Where does blood go from the right ventricle? How does it get to the pulmonary arteries? What's the name of that vessel that's headed towards the pulmonary arteries? Pulmonary trunk, that's right. Okay, simple enough. Then we go to pulmonary arteries, one for each lung. Okay, and those pulmonary arteries become what on their way to the pulmonary capillaries? Take a guess. If you don't know this, you can guess it. Starts with pulmonary. Pulmonary arterioles, very good. And then capillaries. This is where gas exchange takes place. Okay, so gas exchange takes place here, just like it does in systemic capillaries, only in the opposite direction. Okay, what's next? Not quite veins.
Venules.
Yeah, pulmonary venules, then veins. All right, then where does it go? Left. Atrium, right? So we're not going to talk extensively about this, but I want to assume that we all have this background, okay? So we will certainly talk more about how flow of blood through here impacts gas exchange, the absorption of gases during gas exchange, okay? When we think about the pulmonary circuit, think back to what we learned about previously. Let's keep in mind how these factors differ. We have flow, pressure, and resistance. How are they different than in the systemic circuit? What about flow? The flow of blood through the pulmonary circuit. How does it compare to the systemic circuit? It's the same, right? It's the same 5 liters per minute as goes through the rest of your body. Okay, what about resistance? More or less resistance? Less. Why? Doesn't have as far to go. Remember we talked about 3 factors that contribute to resistance? What were they? Length of blood vessels. What else? Radius. Viscosity, right? Watch the table. Viscosity is not going to change, right? Radii, they're not any smaller over here, right? But, yeah, we have a much shorter length of vessels, right? So we're pumping that blood through much less vessel length in total, okay? So we're going to have much less resistance. Okay. And the pressures, as a result of that low resistance, low, much lower, okay? So a mean arterial pressure in the systemic circuit is going to be about 90 millimeters of mercury. Here it's more like 20. Okay, much lower. Okay, last little summary material for you before we jump into ventilation. The last thing, of course, where all this is headed towards the idea of gas exchange, right? So at the end of our airways, we have alveoli. And what distinguishes an alveolus from something in the conduction pathway is that we have very, very thin cells, right? So they're not columnar, not tall epithelial cells. What kinds of epithelial cells would they be? I heard it. Squamous, right? That's the term we use. Very thin, flat cells. So when we zoom in here, the cells that make up the alveolar wall are the pneumocytes. Okay, so type 1 pneumocytes here. Really, really flat. Okay? Really, really flat cells. Why is flat good? Not inherently. What's good about it? Surface area is very important for gas exchange, but being flat doesn't impact the surface area. No?
Would it make it easier to exchange?
Yeah, remember we talked about things that affect the rate of diffusion back in one of the first, yeah, so the distance it has to travel to get through the membrane is a major impactor for diffusion rate. Okay, so diffusion goes quickly through something that has a short distance, so the distance between one side and the other of these cells is very, very short. All right, So we've got these little air sacs with their very, very thin walls, which allows diffusion to work very, very rapidly. Okay? And what's surrounding an alveolus? What are these little donut-looking things? Those are capillaries, right? That's a capillary. So if we take a look at this apposition of alveolar cells, right, and a capillary wall endothelium, both of these are squamous epithelia, right? Really, really flat. So the structure and function is obvious here, right? We have very thin walls on both accounts, right, which allows diffusion to work rapidly. Okay, so we'll discuss how this plays out later on, but just so that we're all kind of familiar, at least, with the basic anatomical and functional characteristics of the system. Okay, that doesn't look right. Okay, close your eyes. Okay, close your eyes. Keep them closed. I'm not fooling anybody here. Something went wrong. Okay, sorry about that. In summary here, what we've got are all these different processes that we've kind of run through so far, and with each day that we go through, we're probably going to spend pretty much one day on each of these principles. Okay, we'll bleed into the next lecture a little bit with ventilation. Okay, so you can expect to get to know the system pretty well. Okay. Any questions before we move on? Yes. Does the squamous epithelium help? Make resistance lower? No. That's a great question though. It's what we're talking about with the squamous epithelium is that the distance across from the lumen to the extracellular fluid on the other side of the cell is a short distance. Okay, but when it comes to providing resistance to blood flow, are you talking about blood flow or air flow? Yeah, blood flow. It's the surface area on the inside that matters, right? So it's that surface area on the inside that's providing the resistance. Think of it as friction, right? That blood is encountering the vessel wall. Okay. So how thick the cells are, it wouldn't play into it. Okay. But yeah. Any other questions? Okay. All right. How many of you remember Gen Chem with a lot of fondness? Really? All right. Remember this thing? Oh, you're groans. Okay. The ideal gas law. Nobody's favorite. Okay. What is the ideal gas law? What does it tell us? It tells us the relationship among the various characteristics of gas, right? Okay. So we're not going to go through this. You're welcome. But I want to point out two things. P stands for pressure, and V stands for volume. Very good. Okay, it's not so bad. All right, so we can see that there is an inverse relationship between these variables. Okay, and this is the thing that I want to point out to you. Okay, so we will actually come back to some of this and discuss it a little bit further when we talk about gas exchange. Not too much, so don't fret. So pressure and volume have an inverse relationship. Okay, and this is how we derive Boyle's law. Okay, remember Boyle's law. Okay, so we're going to focus on these two variables. Make it very straight to the point. So when we change a volume or a pressure, the other variable changes inversely. Okay, simple enough. Okay, so here's a little illustration of a bunch of molecules bouncing around in a gas. Okay, in a chamber, and if we compress the chamber to make the volume smaller, right? We have the same number, same N, the same number of particles, but in less volume, what's going to happen to our pressure? Raise your hand for decrease. Raise your hand for increase. That's supposed to be good. Yeah, it is going to decrease. What's the principle behind that? What's the chemistry principle behind that? You got all these molecules closer together. What's happening? They have more interaction with one another, but importantly, there's more interactions against the container, right? And that's how we measure pressure. Okay. All right. So what about the opposite? If we take the same gas, the same number of molecules, and expand the volume, pressure goes down. Okay. So this is a very basic principle, and it's how our lungs work. Okay. So when we start to talk about ventilation, we are talking about this principle of changing the volume of the container, which leads to a change in pressure. Okay. So what volume are we changing? Lungs, right? Very lungs. Okay. We're changing the volume of our lungs. That's right. Okay. See if you can answer this one. This is all right, one person probably. Okay. Somebody tell me, the most common answer here is B. Anybody have an explanation why you picked it, or maybe why you picked the other ones? Yeah.
So, the correct, relationship between volume and pressure is, all of them are the correct relationship. However, you can't really directly change pressure in your lungs, so you have to make do with volume, so that's the thing that would have to change first.
Okay. Yeah. So volume changes. Volume changes are going to precipitate the pressure changes. Okay. Anything else?
And then air is similar to blood in that the pressure difference is what actually drives the movement.
Right. So you remember this last point she made is great. She said that air is like blood, and I'll add it's fluid, right? And the pressure changes, the pressure differences are going to drive movement, right? What do we call that movement? Flow, right? Okay. So remember delta P, right? So delta P is going to drive movement, right? So yeah, you're absolutely right. So we are going to have volume increases that lead to, according to Boyle's law, a drop in pressure, right? And that drop in pressure relative to the atmosphere is going to be what draws air forward, right? Okay, great. So in order to do this, we have got to talk about how we breathe, and it's simple enough, right? Don't we just increase the volume of our lungs and it's end of story? We could end the lecture here. Don't get excited. It actually is a little bit more complicated than that. Okay? All right. Here's a little bit of anatomy review. How many lungs do you have? 2. Great. That'll offer you something. Okay. 2 lungs.